Everybody. I'm Jessica Rodriguez. I'm the Data Science Institute Industry Engagement Officer. Thank you for joining us today for our iCubed, which stands for Institute, Industry, and Innovation. These are seminars that connect our industry affiliates to our students and the larger Columbia community to explore topics at the forefront of industry. We invite data scientists, engineers, or researchers from our affiliates to give a talk about a recent project or case study. During these educational events, we encourage attendees to ask questions via the Q&A feature, the chat feature today. Just pop your questions in there. Today, we have a data scientist from General Electric, GE, joining us. Today's talk is Humanity in AI, Automating Epistemology, Trust and Explainability, presented by Dr. Paul Ardis, who is the Machine Learning Technology Manager at GE Research. Welcome, Paul, and thank you so much for joining us today.
Thank you very much. Glad to be here. So I'll be talking about a few different things as we go through, but the main concepts are going to be around, as you can see, epistemology, trust, and explainability, and what that really means from an industrial machine learning setting. So coming from GE, the emphasis here is going to be very heavily focused on the different settings that we're working in, but I hope that you can see the applicability to all of the sorts of problems that you may see going forward. So first things first, epistemology. The basic concept here is that we're looking at what is different between the concept of justified belief and opinion. Fact, in that it is something that you can back up with evidence and justification, versus something which is your opinion, your take on something, but not necessarily backed by any sort of objective, quantifiable evidence. Then trust here refers specifically to the acceptance of justified belief. That's the case where we have people that are willing to accept that what you provide as justified belief is sufficient for their purposes, and that they believe that it is comprehensive for their need. And I'll talk about what that really means from a human perspective as we go into this too. And then explainability, which hot topic in AI in general, but here what we're really going to be talking about with it is that it's all about how do you use explainability to encourage trust. And the intent is that systems that have an explainable attribute to them for the purposes of making that transparent transfer of the supporting evidence for the decision making that you're hoping to instill. So, like I said, I'm coming at this from a GE perspective. So we do three main things as a company, and you'll see throughout the slides a lot of emphasis on those three things, which are we generate electricity for the world and move it around, and by and large, the emphasis there is on the future of the fully renewable grid. So how do we get renewable energy out in a way that we have massive distributed generation, massive distributed storage, a wide variety of different needs? How do we have systems that enable that effectively? Second is the future of flight. So GE, being a major jet engine manufacturer, is looking at how do we get to a carbon neutral manner of moving around the world. How do we step into hybrid flight and then fully electric flight for the good of humanity? And then beyond that, it's healthcare, and how do we take healthcare concepts and increasingly move things into the home as we continue to increase our expected level of care? Because the intent there is to allow for people everywhere to be receiving top-notch healthcare without any boundaries or concerns. Now, obviously, all of these sort of inherently speak to the needs for certain degrees of human trust in the data, but I'll be talking about human trust in the algorithms specifically as they get developed, and what they're aiming to do and how we accomplish that. So one example of some work that GE's been heavily engaged in is attempting to help to curb wildfires in California by way of vegetation management for power companies that are out there. So put simply, understand when things are getting to the point where something needs to be done so that we don't have to worry about the possibility of high voltage wires being the potential instigator of a new wildfire. Now, the critical nature of this, of course, calls out for the idea that we have something that is high confidence and high competence. But beyond that, in order to have acceptance by the grid authorities, and more so, to have a willingness to issue people when there are, thousands to millions of miles of transmission infrastructure that needs to be inspected, the understanding of the degree of that and the justification for the issuance of personnel to do something actively becomes a critical aspect of it. So the work that we've done there is very much focused on what are the pieces of supporting evidence from a visual perspective that suggest that some action needs to be taken. And that's actually an integration of satellite data from low altitude visual survey, where available, additional drone footage, which is one thing that we can issue additional requests for. But essentially, can we take all of those pieces of evidence, automatically determine that we have a sufficient amount put together, and provide human decision makers their justification to issue people out there to get clipping of trees and making sure that things are going to be clear and okay. So that work is underway right now, and it should give you a sense for why we're doing it. And like I said, I'll get into some of the how and the real algorithmic details in just a minute. But another good area to think about this is a project that we have ongoing right now for ARPA-E, which is essentially a major government research group, in this case specifically focused on ensuring continued safety, reduced operating costs of nuclear power in the United States. The intent here being, we want to make sure that we can have something that can help bridge the gap between current very carbon expensive, carbon detrimental generation to a fully renewable future by way of nuclear. And one of the key factors in that is reduction of operating costs. So can we ensure safety by making it easier for everything to be watched and guaranteed? Can we provide trust in nuclear power at reduced cost? And a lot of the emphasis there then is on this robustness of AI methods. So it's not just that there are things that have eyes on everything which must be watched from a compliance or even beyond from a efficiency perspective, but that it is sufficiently encouraged and provides enough understanding that people can take a look at that and say that they personally feel comfortable with it, but furthermore, they're willing to understand exactly what they believe the expected risk would be for any area which is being monitored. So a couple more areas where we're working on this, and I'll highlight these two because I'll go into some detail about the actual programs themselves and the resulting tech. One of them is for service analytics for renewables. So essentially, when we've got wind turbines that are out there and we detect that something looks not right from the data that we're getting streaming back, we want to talk immediately with the customer and get to a situation where they have the shortest possible outage, the limited amount of cost. But at the end of the day, this is a conversation where the customer needs to be convinced that something needs to be done, and frequently in a highly proactive fashion. It's not necessarily that a blade has visibly cracked or that there has been something that absolutely must immediately be taken care of because everybody can see it. Now, instead, this is something where we need to be able to generate a disposition report which provides supporting evidence that we have captured a reasonable and meaningful signal that we have tied to past examples and can point to the concern as well as what the anticipated next steps and consequences of not taking action, what that looks like. The intent there is that at the end of the day, they have to say whether or not it's okay for a GE field engineer to go out there and climb, to go up and take care of things on their equipment. And that's not something that is necessarily trivially done. But we're hoping to drive down a lot of the inefficiency, make it faster and easier to get to these sorts of conversations. So that's really, again, everything so far has been very focused on the human justification. But even in an fully automated setting, where we talk about a deployment where we anticipate that there's effectively sort of a closed loop behavior system, so such as a fully autonomous vehicle, in those cases, the aspects of trust are necessary even for the internal operation of the system, beyond which, of course, explainability and trust in safe operation of the system is going to be a requirement. So we have an ongoing effort with the Army Research Lab, excuse me, under the Scalable and Robust Autonomy Program, or SARA, which is focused on being able to have a system that learns to recognize things it does and doesn't know it can do, such that you could drop it into a totally different terrain and it'll work fine. Because, of course, the intent here is that the Army wants to ensure that they train something and then they don't have to worry that they have trained it on exactly the same sorts of things that we'll see. But likewise, we care about the exact same need, because we can't take the service robotics that we have or the inspection robotics that we have and train them at every customer site. We need to be able to have something that has a sense of the ability to transfer effectively with high confidence and with an understanding of the areas where it is failing to be sufficiently confident in order to go back for additional data capture, for human in the loop, for alerting, for anything on those. So I'll show you what that actually looks like in just a minute. But I'll just emphasize that overall, if we think about where AI is going as a society, we're not reaching a point where we necessarily expect that AI is going to take over for human activities. No, it's more a situation where there are more and more things, like talking to your phone, like talking to a home device, where you expect that you will be having an interaction with an AI system. But at the end of the day, it is human decision-making and human action that is going on. Life happens, and the intent is to have systems that we trust that work within that, and that we can develop things that they know enough about themselves to be able to really tell you just how well they can do their job, so that you can decide whether or not it makes sense to have them be that extension of your life or not. So when we think about the science of certainty and actually quantifying uncertainty, I'm going to talk about epistemic classifiers here. So the idea here for an epistemic classifier is that you have justified belief. So essentially, it is coming up with the background, the material and evidence that allows you to determine which region you happen to be in, specifically the region of trust, where you have justified belief that you know the answer. So you are able to provide an output for the system that matches all expectations of everything that you have seen and everything you believe as a consequence of that. The region of ambiguity then is areas where you may have conflicting evidence. You may have training examples that are incomplete, or which have labeling or alternate markings that do not agree with each other. And as a consequence of that, having a belief system that is built on the integration of that, it provides an area where you believe that you may know, but you cannot say with full confidence that you do know. And I'll talk about the tunability of this in just a minute. But then also critically identifying those areas where you are beyond the bounds of anything that you have seen in the past, where you know that you are intending to operate beyond existing justified belief and are in that, as a consequence, region of extrapolation. So when we think about an AI system, the goal is, can we come up with crisp understanding, crisp boundaries for these three regions based upon the data that we have? So in the Sarah program, just so you can really kind of ground this and see how it works, it's pixel by pixel understanding of what things are. Can we do multi-class classification at the pixel level based upon everything that we've seen historically? The idea is you can use some local information in the terms of, you know, having a convolutional set of features that you've run to say, okay, yeah, well, it's not just because it's green that it's grass, but it looks like grass in that region. But critically, it's trying to determine pixel by pixel, do we know what that is? Do we think we know it, or we may know what it is? Or are we confident that we don't know? Now, the critical things here is that for each class, we are essentially determining each of the regions. So we may know that we are about to travel over grass, but we do know definitively that it weren't, for instance, not going to run into a tree, given our justified belief in examples. Or that we know that nothing that we see in our justified belief, nothing that we see in our supporting evidence suggests that we are about to traverse over mud. So the idea is that at the end of the day, the system then is encouraged, okay, this is sufficient to suggest that we can go ahead and travel there. And here's what it looks like. So this is an example of fully autonomous operation at GE Research Campus in upstate New York. And you can see driving around, we've got grass and leaves, we've got trees, we have various things in the area. The whole point of this particular jaunt was just, don't run into something. Don't hit a tree, don't hit a car, don't run into a person. And as you can see, the map and the exploration on this is constantly changing. On a frame-by-frame basis, we have different levels of certainty in what we are seeing. It's showing the most probable, labeling it for each particular pixel. But the critical decision that's happening under the hood is whether or not we've actually believed that we do know that it is something that is traversable. And you can see that essentially, even in situations which can get somewhat hairy in terms of the kinds of things that could be run into or rolled over, confidence in that allows us to keep moving. And that's the goal for any sort of system like this. It's, can we have sufficient confidence internally and then use that for the action that needs to be taken? So here's kind of the mathematical breakdown of it. It's based upon the concept of support. So if you look in a region around your new sample, do you have training examples that provide class labeling that justify what you believe to be the output that you should be providing at that point? So you could imagine that if you're talking about a system that is basically a naive reasoner, that consensus or majority opinion could provide a numerical best guess. But, excuse me, it is the fact that you have overwhelming and complete consensus within the support region that determines whether or not you will provide an answer that says, I know, or I may know because there are disagreeing elements, or I don't know because there are no supporting elements within that region size. So if you take a look at the graph down at the bottom left, it's an interesting idea here, which is this, just for an example data set. We follow the orange curve as it goes up. You start by saying that you effectively know nothing. You You cannot say with confidence that you know anything, because with a support that is infinitely small, there's nothing that is within the region of any of your new test points. But as you go forward, you get more and more confident that when you are making decisions, you are making decisions based upon the cases where you have seen training examples in a very close neighborhood of what you've seen, what you're attempting to determine is your response. So you grow your confidence, you're building your way up in that fraction that where you know. There's a sweet spot of that where you actually are sort of capturing all the critical aspects of the supporting justification for decision making based on what you've seen for your training set. But critically, even beyond that, if you just keep widening it out, eventually you catch everything. And then it's all of your training examples, including conflicting ones. At that point, suddenly you might know, but you can't say with confidence that you know definitively. So to understand how you might use this, right? You can make a classifier where you have aspects of this explicitly extracted such that you are attempting to capture support at multiple layers. So for instance, if you have a multi-layer neural network, you might be looking for support in terms of where you end up in representational space at any particular level in that network. It doesn't necessarily have to be in your raw input, like your original input data space, but in some critically transformed and maybe even relevant and understandable level. So if we're thinking about the processing of various images, this might be something which has gotten to the point where it's, they're class relevant, sort of visually recognizable features of different things. And at that point, you are looking for whether or not you have justified support. So in terms of what we're doing to do this, a lot of the emphasis then is that you're doing meta learning. You're trying to figure out, well, how much does this matter? If I'm doing this across multiple layers, am I integrating it as sort of I know for everything, if I want to provide a numerical estimate beyond the sort of a simple, I know, I might know, and I don't know understanding, how do I provide that? And that's really where a lot of the work is going on right now in terms of moving this and looking at specific applications. But you can certainly imagine that the whole point of this is to try and get further and further away from any system that is operating in a way that is naive and assumes it's always right, or on the other hand, figures that it may always be wrong and basically always has to be checked by a person. Because the goal here is that you can take those regions of very high confidence, even with perhaps reduced support regions, but sufficient evidence within, that you believe that you can automate a system within those bounds and trust it to be okay. So if you think of, for instance, an area where we often will see this come into play. Many people who are listening to this, or in general, folks who are involved in AI, are familiar with MNIST. MNIST, it being a set of data sets corresponding to the recognition of written characters, something that came out of needs for the Postal Service and other various areas. If you think about it, when we talk about OCR, that's very much an area where we would love to say that we want to only focus on the cases where we have potentially conflicting support. It's only when we have something which, hey, that might be a 7 or a 9 that I want to talk to a person about it. Because a system like that is expected to operate with high confidence over the vast majority of its data. So the emphasis on the work is always on tiny little incremental improvements on the data set, because we know that the need here is to try and drive down the human decision-making element, drive down that human cognitive load that's going to be needed, or even accept an answer which might be wrong, but think that you're going to be right most of the time. Well, I say it's better to be right all the times you're automated and go and talk with the person the few times you're not sure. That's probably a better solution. And when we're talking about anything for critical infrastructure, obviously, safety and everything else being a factor, that is how we work. So when we think about this sweet spot operation, and you think back to that graph I've shown here in the top right, and kind of tagged for a few different things, it's all about how do you play around with this hyperparameter. And in doing so in a way that you will necessarily make completely transparent to anyone who is going to accept the final application of this, what that hyperparameterization is. Because if you think about it, it lets you drive down, get rid of your I don't knows. It lets you wipe out false alarms. But if you go too far, you're back to having a system that has to always talk to a person. So your selection of that allows you to do very interesting things, but at the end of the day, you're going to need to have that be something which a human is going to accept as a reasonable way that you have determined your objective justified belief in your system. Does it need 10 examples for its training set that it can point to? Does it need to have 100 or a radius that suggests that there's nothing, even 10% dislike it, that disagrees with it? Those ideas are where we are pushing things. And I'll go back to thinking about what we are doing as a company and why we care about this. When we decide whether or not we need to be taking action with a customer for a repair of a system, they want to be able to see that we have seen cases like this, and we can point to them and say that hey, this is the same, and we can tell you why. They want to be able to understand that if they're going to fly, they're flying safely, or that if they're going to get a diagnosis that is supporting a human doctor, or eventually helping to provide some triage at home, that those are things with very, very high confidence. And that if there's any potential for uncertainty, that is going back to the source for whatever that original expertise might be. So have a number of different data sets that we have explored with this. It's worth noting that this concept of epistemic classifiers is really catching fire. And I do very much recommend that you learn plenty about where it's going today. I'll point to papers at the very end of this that talk about where we are hoping to take it in an industrial setting. But certainly you can imagine there are other areas as well. Now, moving from this base concept of an epistemic classifier, justified belief, and having the concept of support be a critical aspect of your explainable hyperparameterization, I want to take that a step further and talk about causality. So explainability, specifically in the realm of causality, is particularly important because these are systems where we are attempting to suggest that it is not just that we have seen like examples that numerically correlate, but we believe that there was a sufficiently confident matching sequence of events or sequence of signals that provides a recommendation for action. Now, obviously, the difference here is that it's often easier to convince a person that there is a causal path between pieces of evidence that justifies something, but it may also be trickier to ensure that you were doing so in an objective fashion given limited training examples. So the thought is, how do you structure an algorithm for this? So we've been looking at this specifically. So first under some initial work for the Department of Energy, but now expanding into a number of different programs that we have at GE. And the thought is that the concept of the causal links that are being learned, you can have a system that has those implicit in some fashion that is not necessarily easily interrogated by a human, but useful from a statistical perspective, or you can have a system which attempts to make it something that you can explicitly expose to a person and get their confirmation on in order to use. And we're doing much more of the latter. So if you think about what happens today, if you want to have a system that is going to find things that you know are sort of issues, or that pick out anomalies from the known concern issue areas, you have a subject matter expert. They come up with features. They tune or tweak some standard set of features, and you make a rule base, or you make some sort of classifier that runs on top of that. That's sort of the simplest and easiest way, and that's the start of where the connection comes with the human expert today. But ideally, what if you could have a system that said, well, we're going to take this as a starting point, but we're then going to create an explicit causal map. So we're not just saying that it is the correlation of the existence of some of those features with some data that you see that suggests that there is a concern, but really that we've seen an explicit causal web. And this in particular being a construct which is looking at the continued correlation between features or lack thereof. So essentially, whether or not you have, say, temperatures and pressures that trend similarly and match expectations, and then deviate, and in particular deviate in a way that is recognizable and uniquely identifiable. So you could think of this certainly in an industrial setting. We explore this for things like loss of pressure in a highly complex system, or inefficiencies introduced in terms of fuel. But you could even see it in domains such as cybersecurity, where suddenly it is these from raw data and passes some of these to humans, to even human experts, to refine. And that really is the world that we live in now for GE, is that where we have systems that are deep causal front end, human expert, and deep causal back end as well. The goal here is that all of the above is being used, but we are ultimately trying to make use of the human expertise as optimally as possible. Like you don't have an infinite amount of human time to look at things and confirm whether or not those are real concerns, or to say that I am a long-term multi-decade designer of gas turbines and can confirm whether or not a particular feature makes sense, or that if I saw sequence events that might mean that I'm seeing early light off. Now that's something that I want to make as easy as possible for them to confirm, because we don't have an infinite number of people or an infinite number of time, but we have plenty of compute. So a lot of where we're looking right now in terms of explainability is deep causal systems that can tie into a human. And here's an example of sort of the things coming together. So this is looking at operation under various ambient conditions. You can see training examples in red that are sort of suggesting the areas that we know. And movement away from those gets us to a expectation that where we don't know. We're operating beyond the bounds, and our system our epistemic classifier on top of it would say, we can say we have reached a level of incompetence, but then on top of that, we want to be able to capture that, and we're going to pass that to a causal net, and we're going to try and identify, okay, well, can we use this to make better features, to figure out, for one, what our training set should look like, but also can we capture and distill out the critical aspect of that deviation to say what led up to it and what was the sequence of causal events, and are they explainable for a human? So we do this for everything from wind turbines to solar panels to Anything that moves people, keeps the lights on, keeps people healthy. And it's good to think about, okay, well, so what do you do about that? You make systems and they are reasonably explainable and they have a sense of confidence and you're working with a human to update them. But at some point, they might not work and you have to make updates. At that point, it's worth noting that here the critical thought is, okay, well, we'll have this idea of a system which is dynamic. We allow for models which can be updated on the fly, potentially without any human being notified that we're doing it. But we need to have auditing. We need to have the ability to run it backwards and say, okay, even within the operation in the relearning of these systems, what happened? So the simplest way to start from is to just think a two-learner system. You've got essentially a long-term, stable system that you've trained from some starting point to forever. And then you are constantly retraining a short one as needed. You say, I have reached a point where I am beyond the bounds of my competence and confidence. I want to have something which is focused exclusively on the dynamics of the window that I'm operating within now. And you trade off and flip between the two. So by having a system like that, and by having an indication of when you are making that decision making and flipping between those, that allows you to understand that you have not just sort of a track record of confidence as you go, and as much confidence in the model that you are using at any point, whether you have to rely upon something that has limited support short term, for instance. But when did that happen and why? Because then we're not just trying to capture like the dynamics that led up to and can be recognized by a system in the future. But if a human wanted to look back and audit that and know what's going on, are they able to tell that we had big jumps that caused retraining? Or did we have sort of a gradual progressive change? And this is a couple of examples of running this for understanding the expected output of of power generation, traditional steam turbines over very, very long periods, where they may slowly degrade because of wear. They have regular maintenance at certain points, but we want to be able to capture essentially the dynamics that correspond to them so that we can say, okay, these are the models that were being used with this confidence. Here's why and when we changed. And like I said, at the end of the day, we're looking at this so that we can have something that we're able to do a lot of this exploration and training in an offline safe fashion. We're doing a lot of this, the machine learning research, the data science activity, not expecting that within 5 minutes or something it's going to be put on the system. But when we go from something which is being done within the safe confines of the research center and the manufacturing facilities that we work in to something which is going to fly around the world, we need to know and trust that it's going to do it right. So just to sort of give you a rundown of what this is coming from, I touched on some key factors from 4 papers, which I've got the information for here. Be glad to answer questions on any and all of them, but I highly recommend that you take a look at them and some of the subsequent papers. So this is stuff that was in AAAI 18 and after. I'll also point out that it's worth noting we're hiring and we're looking to bring on more folks who are interested in pushing these sorts of boundaries. We're looking to build up our core of machine learning researchers with an emphasis on things like explainability, causal inference, the interactions of physical systems, because we want to make a difference. We want to make the world a safer, better place to live in, and we're hoping to get there with you. At this point, I think it'd be great. If there are any questions, I'd be glad to take them.
We have a question from Shruti. Are you hiring? This chat feature is a little different from Zoom, everybody, so I've got to get used to it. Are you hiring for all areas or specific areas, Paul?
I mean, we're hiring in multiple different disciplines. For machine learning specifically, we are hiring for all areas of machine learning. We've got certain areas we would love that people have an interest in exploring or some experience, but at the end of the day, somebody who is sharp and has that core background could start to explore with us. We recognize that, hey, people don't go to school to learn how to do machine learning for large industrial systems or critical infrastructure. That's not what you get a degree in. But if there's an interest there and people have poked around and they want to explore there, then we should definitely have a conversation.
Wonderful. That actually leads to, well, if people want to drop their questions into the chat, that's great. But a question that we asked during these iCubes sessions are, what would a strong candidate look like? What core skills would they bring to the table?
Yeah, absolutely. So fundamental grounding in statistics and machine learning in general is sort of a given. You should have a sense of the breadth of things that are out there. Like, it's great to know a variety of different constructs. Deep learning in particular, for instance, it's great if you can make a deep neural net. It's even better if you know there are things other than deep neural nets. Because at the end of the day, there are many different things that we will look at for potential tools. And more importantly, we are inventing new things constantly. And so knowing the sense of what's out there to build upon and develop new technologies, that's sort of the starting point as for being a researcher. But thoughts beyond that in terms of what makes somebody a strong candidate for potential hire, especially within GE. It's great if somebody's had industrial research experience or any research experience that you feel has the aspects of that. So the most critical thing here is that often the types of problems we're looking at are the ones where the penalty for being wrong is very high. We're not selling ads. We're not flipping bucks. We're not in a situation where you can accept being wrong 1% of the time, because if 1% of the times that you flew a jet engine, it blew up, that would not be okay. So having had some real core experience focusing on problems that you have seen that are very hard for that specific reason, that's a very good place to start from. Beyond that, of course, ability to learn. Everybody's going to be learning in place. There's no, like I said, nobody goes out of school with exactly the right matching everything. So having a demonstration and a demonstrable ability to learn fast and well is great, And certainly a degree is a great starting point, but anything beyond that in terms of additional initiative is fantastic too. Including if you just stretch your brain beyond the realm of data science and machine learning. If there are other things that you have bridged to from your background, it's great that we know that that's sort of inspired you to make an effort to learn. But yeah, that's really the best place where I would say for starting to look for a good candidate.
Thank you, Paul. Those details are wonderful. Sure, our students appreciate that. We have a question from Alicia. Is GE also pursuing machine learning research in the medical space? Apologies if she missed some of this. She just popped in late, but if yeah.
Absolutely. So GE Healthcare is one of our three biggest business units. So in terms of size of number of people, revenue, and all that, our biggest ones are power, specifically renewable power, aviation, and healthcare. And we do other things. Hey, we still do help make some electric trains and the like. But those are the things that we do the most of. Healthcare absolutely is one of the areas where we do a ton of. Now, that traditionally started out in terms of imaging, in helping to invent the MRI and things like that. But these days, obviously the emphasis is not just on having a good capture device. It's how do you have something that is fast and efficient to help aid a human decision-making process, that you have a doctor or a physician, some technician who is supporting them, some specialist that's able to interpret and take what they're getting out of all this and figure out what the best subsequent care should be. The emphasis there being like, hey, okay, that's a broken bone. That's great. What do you do about it? So computer-aided decision-making and getting towards computer-aided diagnosis and computer-aided prognosis, constantly an area that we were working in, trying to reduce cognitive load, improve outcomes at the end of the day, reduce the cost of operation. And like I said, one of the major emphases that we have when we think about, the future of this beyond even this decade is how do we get it more and more and more of that to folks in home so that you can be as healthy as possible without having to worry about waiting until you're sick or hurt enough that you have to go to the emergency room. And especially for at-risk and elderly populations, how do we make sure that there is that constant sense of continued health and protection?
Awesome. Thank you so much.
No worries.
Do you offer part-time summer internships in GE research?
We do summer internships. We actually do internships all throughout the year. So we can do effectively what some people would call co-ops or whatever, but we can have full-time internship opportunities at any point in the year. Works for us. We work all year round. But we recognize that summers are often the easiest given the program that you folks have got. So yes, I'll provide my information, my email address and everything. Certainly shoot me your resume. I'd be glad to take a look. We're working on putting the official posting out. It should be officially out, I think, this week. If you want to dig into that as well, instead of just emailing me a resume. But certainly, we're going to be starting to gear up now. Thinking we're already working on gearing up now, like I said, to start thinking about spring and summer. And yeah, we typically have about 60 interns at the research center over each summer. Now that's not just in machine learning, that's over the entire digital organization. But we have quite a few interns that come across the at GE research every summer. So.
Awesome. So yes, everybody, if you're interested, please make sure to connect. This particular question about the medical space, there's a follow-up. This student is Alicia Daggle. She's getting her PhD, and she's wondering if she could clarify if this happens at the Niskayuna office, or if not, what other offices it might. Yep. I'm not sure if this is.
No, it's fine. So our primary research facility is in upstate New York. It's 2 hours north of the city in Niskayuna. So Niskayuna is a suburb of Schenectady. We have 1 million people in the area around here. Basically, Schenectady plus Albany. They're like right next door. Mm-hmm. But we happen to be in a suburb there. But yeah, we have right around 1,000 full-time researchers plus additional support staff, tradesmen, all that across our site there. We have additional sites elsewhere, but that is the primary focus there. It was the research center as founded by Thomas Edison, dates back to 1899. Huge research campus, and by co-locating people across many different research disciplines, it allows us to work on a lot of the intersectional problems a lot easier. So in particular, when we think about things that are pushing the boundaries and for AI and machine learning in particular, attempting to get those into non-traditional research areas like oncology, it's a lot easier if I can go down the hall and talk with an oncologist than if I'm trying to figure it out remotely. Now, obviously, pandemic being what it is, we're under conditions where we often not in office. But long term, the goal is to be able to go back to having a mix of remote and in-person work for doing that. Because we found that that's allowed us to move the needle on technologies that we never would have gotten there if we didn't have people who were totally different thinkers from totally different disciplines. Somebody with a PhD in chemical engineering talking with me, in order to figure out something that I'd never heard of.
Thank you.
No worries.
What percentage, question from one of our students, what percentage of traditional machine learning versus deep learning do you believe is used at GE's research team now, and how?
Good question. If I had to guess in terms of a breakdown of deep learning versus non-deep learning, where I would say a deep construct is something that is at least 4 to 5 layers of a neural net in complexity, if we're using universal approximator theorem. I'd say about maybe 70% deep constructs, 30% non. But that being said, deep nets are not one size fits all. The idea of things which are completely, every layer is fully connected. There's no dropout. There's no anything crazy with regards to activation functions or any of that. Pre-processing, post-processing being vanilla. Yeah, there's almost none of that. So truly there is effectively some aspect of non-deep machine learning in all of our deep machine learning as well. So yeah, actually maybe I'd say 60% things that would qualify as a deep construct in terms of at least their complexity. Not everything being structured in exactly that way. I mean, a dynamic Bayesian network, for instance, not exactly the same, but still potentially just as complex. So we do have a fair amount of that. Again, a graph neural net structure with sufficiently complex interconnectedness, or a convolutional construct. So we have quite a bit that would qualify as deep, but isn't just a straightforward deep neural net.
Awesome. So while we wait to see if we have any more questions, I do have a few questions that our students are very interested in from hearing from our industry affiliates.
Mm-hmm.
If they were to work with GE, what kind of data would they be working with? It's usually something that comes up.
Yeah, we work with the real deal, the real data for a large swath of critical infrastructure around the country and the world, and real stuff for real people who are receiving healthcare, anonymized in those cases, to avoid any concerns about personally identifying information, of course. But things that, I'll look at the data for a flight that I took yesterday, that sort of availability of information and depth of it. We have data centers all throughout the world supporting our continued activity for this, and we are often thinking about systems where we'll do local experimentation using resources which are largely based somewhere physically, either at our research campus or in one of our supporting data centers specifically for research. Like we have one in Georgia, and we have one in Ohio. But at the end of the day, we're going to work with the real tons and tons and tons of data, petabytes and beyond of data for whatever the problem might be. Because you get a lot of information, but you've got very important problems. So yeah, we get a lot of stuff. Like I said, our main focus is energy generation for a renewable, sustainable future. The idea of sustainable transportation locally and around the world, and healthcare, increasing quality, reduction in cost, and locality at home. That drives the majority of what we're looking at. So, but data across that.
Awesome. In that case, another question that comes up often is, what does a day look like for a data scientist in your GE lab?
Yeah, so our researchers, we can work an extremely flexible schedule. As you might imagine, even though it's a big company, research at the end of the day is a highly, inspirational and innovation focused set of activities. So it's not like we have standard hours or anything like that. So generally speaking, for what we do, we have projects that are between usually about 6 months to 2 years in duration, which are often, they're split 50-50, where we'll be working either directly with and funded by one of our business units. So working with a team there. So a team of their data scientists and their product experts, their application specialists, or be working with, say, the different national laboratories or government agencies, National Institutes of Health, Lawrence Livermore, and other groups. So like 50-50 government supported versus business direct. And in those cases, the emphasis is that we're looking at things that are, first, what starts to get to an answer for them from what we know today, but then where do we need to push the boundaries of the fundamentals of knowledge and tools and capabilities to get them to something that could potentially solve their problems. So we'll look at things that are completely off the wall. We'll work with those teams. So our typical day, you'll work with your various teams. Typically, we usually have 2 to 3 digital AI folks, whether they be core machine learning people or maybe computer vision specialists, or there are a number of different sort of sister groups within the organization as well. Whether the idea is that we'll have like 2 to 3 of those experts working with, like I said, a variety of experts from other technical disciplines, both from the research center as well as from either government agencies and government labs, or from our different business units. So working with them on that project work, and then just some general additional exploration time for broader things too. We have things that we're looking at that are sort of blue sky concepts beyond the bounds of anything that we may have as an existing project. So about 10 to 20% of our time on things that are like that.
Thank you so much. I do want to make sure that everybody saw that Paul does have a slide with his email address on. We dropped it into the chat again, and also his LinkedIn was dropped into the chat by Alexis. We want to make sure you have the opportunity to connect if you'd like to. We do have a follow-up question from Alicia, but it's a little bit detail-oriented. It's about obtaining data from the machines that GE, because of medical imaging, does that go directly to GE, or do you have to go through the hospitals? It's about what the data resources are from machine learning.
So it's perfect. It's a good question. And the best way to think of it is that for all of our applications, if GE made a piece of equipment, it will always phone home about its capabilities. So we're always, an MRI machine will tell us if it thinks it's going to break down, so that we can ensure that we have replacements. We have a program called Tube Watch, which is looking at, when do you have CT tubes that are going to need swapping out, like that kind of activity is something that is sort of a direct stream. For anything which is more sensitive, or where the data is more critical for the customers or the people of society as a whole in general, it will often go through a secondary along the way. So we have ongoing agreements with, for instance, all the airlines who fly jets with GE engines. We have so we've got agreements with them, various hospitals and hospital networks throughout the country and throughout the world.
Are internships available to graduate and PhD students specifically?
Internships must be for folks who are in PhD programs. We can't take people in master's programs for an internship, unfortunately, but we can take master's grads for potential full-time hire. It's just a quirk of how our system works right now.
Okay. But we'll have plenty of hires to work with sure. From our master's program. And I think there's a question about scheduling that is a little specific, but we have several thanks in here for the excellent presentation, Paul. Thank you so much for joining us today. We really appreciate your time and your insights into GE and into your hiring. If anybody would like to connect with Paul, please feel free. And thank you very much, everyone, for attending today.
Thank you. Have a great day, everybody.
Thank you, Paul.